Okay, good morning, everyone. Let's start. Today, this is the last topic that we are going to cover. So that is center management, or you can call it a resource management. My PhD thesis was on resource management. So this work is mainly on some of the works I did during my PhD studies, and in general, what is resource management and center management. Okay. So as we discussed in the first class, look at this diagram. This is for online. Okay. There are two kinds of resource management. One is online, other one is offline. Okay, so two kind of resource management are there. So resource management is how you optimally use the resources that you have. When you come to resources, so before when you say resource, you can say any, for example, sensor. For example, one is sensor. If you have sensor, so you may need to have say pointing angle, for example. So for some of the radars, you can, for a phased radar, you can decide where to point. That is a resource management problem. So you would decide, okay, this time you point here, then move here. So that is the resource management problem. I will talk about many sensor management problems, then platform. Platform means aircraft. For example, you have a radar on your aircraft, then you want to find the path plan. Okay, so path plan. What is the optimal path you have to take in order to achieve something? That's path plan, right? Or someday you want to save energy, for example. In some cases, the battery is limited. So how would you save the energy so that you can use your sensor for longer time? Okay. Online means if you think about a tracking, right? Say offline means, let's say you have a for loop k equal 1 to k and n. Okay, this is how you do the normal tracking, right? If you do something over here, that is online. If we do it here, that is kind of offline. You understand that part? So before we do the tracking, if you do something, that is offline. And if you do something inside every loop or once in a while, that is online. This one will not use track results. Okay, this won't use track results. This won't, because there's no track results at that time. But the online will use the track result. Is that clear? That's the major difference. Offline won't use any track results, and the online will use the track result. One example of offline might be, say you want to have autonomous vehicle, and in which you want to mount the cameras on the car. That's an offline problem. Or radar or LiDAR, whatever it is you want to mount on the car. So you would do that at this spot. You would do it here. That is offline problem. Then once you do it, for example, if the beams can be switched, then that's an online problem. Okay. Or for example, say you want to fly between Chennai and Patna, so then they want to plan for an airport. Then finding the location of airport is like offline problem. We have to have the airport. Once you define the airport, and every time, say, depend on the weather and so on, you want to change the path of the aircraft, that is kind of online, right? I believe the difference between online and offline is clear. Is that clear? Right? So I repeat that offline means we do that without any tracking information, but you would consider possible scenarios that can happen. For example, deciding number of sensors to use. That's an offline application, right? So you want to buy a sensor, what quality of the camera that you need to buy? That's an offline resource management problem, right? So if you want a certain accuracy, say you are given a task and they say that you have to cover 100 kilometers, and the accuracy should be error should be less than 100 meters. If this spec is given, then you can decide what kind of radar to buy. Is one radar enough, or you want to buy two radars? And if you buy two radars, where you place them, that is an offline research management. Okay? Oh, yeah, but in this one, mainly we are going to talk about the online rather than offline. Okay? So what we are going to do is mostly, once you understand that, in the resource management problem, at least in the online one, what we are going to do is, you give the tracks, then the sensor manager will give the action. What action to do? Okay? Such that okay, so you want to either minimize the objective or maximize the objective. Usually, our objective could be, at least in this work, the objective is CRLB. So that is minimizing the CRLB. That is same as what? Reducing the error covariance. So that is the objective. So you want to reduce the error covariance. I said you want to manage the sense. Okay. Before going to the details, could you give us a quick example of that? Say you have a prayer. This is a prayer. You know, the target can be anywhere here. So you can have only one angle only sensor. You have two options. You can put it here. You can put it here. This is location 1, location 2. Which location would you prefer? Assume the distance is the same. Okay, assume the distance is D, and that's the same distance and 2. Which one would you prefer? So this is a resource management problem, right? So the prayer covariance is this. I want to use one sensor, this or that, so that next time my error is small, much smaller than the other. Okay, which one would you pick? One. Oh, why do you pick one? I said sensor is angle only, okay? So you have to keep that in mind, angle only sensor. If it's an angle only sensor, if you use one, you would expect something like this. Okay? And if you use this one, you expect something like this. Okay? So such that way, so if it is larger here, it's better to use on this side so that the intersection becomes smaller. So that's an intuitive idea, right? So we are going to do that to CRLB, but intuition is there. If you know tracking prayer, the covariance, you want to pick a sensor such that it's eliminated. Okay. So this is what we talked earlier, right? So you could have multiple sensors or platform. You have a tracks, all the tracks, right? Then you give it here, tracks and the covariance. Then it gives an action, what to do. Okay, that is the basic resource management problem.
Track you mean data, the pairing track or the actual state estimate?
You repeat that?
In the case of pairing only sensor, by track, you mean the filter data?
Actually, no. In that example, I mean this track is in x dot y dot. Okay, track is always here. The measurement is here. Okay, so I think you have multiple angle sensor. You can do the localization, and you can use that, right? So, for example, this is what this is what I'm going to mainly talk about it. In this one, these are angle only sensors. Okay, all these are angle only sensors. But you can use all of them to triangulate and do the tracking in the Cartesian coordinate. Okay?
But if you consider only angle only sensor, not two, not multiple sensor, in one it could be receiving from multiple targets. So, multi-target tracking for angle-only sensor in a single sensor, or that can be used nearest neighbor. Like we studied nearest neighbor CMKF for R theta measurement. Similarly, what is the approach to be done for single angle-only sensor? Can be used and then.
Or like, even if it's angle-only sensor, we can use nearest neighbor. The main problem is track initialization. Once you initialize the track and if you do the tracking properly, after that, same as radar. Okay, so for example, somehow you manage to bring the covariances here and there. Then if you have an angle-only sensor, you can do the nearest neighbor. You have one angle here, one angle here, here. Then you use the nearest neighbor, do the association and filter. But the main problem is that it won't be small like that. Most likely it might be like that, right? The covariance of that track. That's why it's a little harder. It's mainly about observability rather than the actual tracking problem, right? So, yeah, you have to bring the observability by making maneuver on yourself. Then your covariance has to be small. Then the nearest neighbor is not a problem. But if your covariance is large like this, and if you have two targets here and there, that's hard. But if the targets are in different angles, okay, easy, right? Okay, so anyway, this is not about resource management. You are talking about tracking, right? Filtering itself, right? Okay. Okay, as I mentioned, sensor management, resource management include many things. Sensor selection, selecting the sensor. In this one, in this work, what we have is sonobuoys are deployed from aircraft. Multiple sonobuoys are deployed, but at a particular time, you can pick maybe only 10 of them. Okay, so then the question is which 10 to use so such that the targets are tracked accurately. That 10 is limited by the bandwidth that we have and also the battery, right? So you don't want to unnecessarily use all of them. But in this case, the problem is sensor subset selection. You have given multiple sensors, you have to select subset of it. That is one of the resource management problem. Sensor modes. I don't know if you know about the military radars, the multifunction radar that can have search, track, and several modes are there. So in that case, what mode you want to be active in a particular time, right? That is one. Other one is a search pattern. That means in the phased array radar, you can say that, okay, point here. Then next time you can say point here rather than simply rotating. If you have radar, say for example, your tracker say one target is here, another target is here, the coordinates are here. Then you have to decide how to assign the beam such that you continuously track the target and also you detect a new target. That's well. Okay, that's the beam pattern assignment or beam selection as well. And another one is optimal sensor placement. So in one of the work, what we did this in this same problem. So first problem, I consider that you have only 100 sensors already deployed. Which one to pick? Another problem is that in certain area you don't have sonobuoy. For example, say sonobuoys are here, and here. And the track is going like this, another track is coming like that. So you are asked to deploy one sonobuoy, one extra sonobuoy. Where would you deploy? Right? I don't know. So for example, if you want to pick a two location here and there, which one would you pick? So that is a sensor placement problem. We have to place the sonobuoy such that the overall tracking accuracy is better. Okay. Optimal sensor selection, I already mentioned about subset selection. Other one is a path planning. In this work, I think actually we did that too. The problem with passive sonar, this is a passive sonobuoy. The problem is that PD is really low. Because if the enemy wants, they can be quiet. Okay, so they can turn off the engine sound so that you can't detect any angle. In that, what we did was there's an active sonar here that only send transmitter. You can say that transmitter. So this become a bistatic. So it goes here, comes here, goes here, comes here, goes here, comes here. So then we had a helicopter to hang this active sound everything. Then you can have an optimal path for this helicopter. So move around. The passive sonars are so fixed, but this helicopter can move so that your transmitter can move to different locations, so you can have a better detection. Right? In that case, what should be the optimal path of the helicopter so it's such that your detection will be better. Okay. And we already talked about offline. And the other one is the waveform selection. So some of the radars can support multiple waveforms. So you can pick a particular waveform to use. With that waveform, I think that will change the sigma R or the P. Okay, it depends on that. You can change this. This is other one is a power assignment. I don't know how many of you know about radar. In radar, you can change the transmitter power or the PD or SNR or PD, the function of the transmitter power. Right? So by changing the transmitter power, you can increase the detection probability, but you don't want to unnecessarily increase the power. So what should be the optimal power to use? Okay. Time on target selection means sometime, but in this beam selection, what we say is that if you want to assign the beam, I say 1, 1, 1, 2, 2, 1, 2, 1, something like that. In this case, I say that okay, assign the beam to 1. Okay, next time also assign it 1. That is like how many times that you want to keep that beam on that particular target. Okay? That target revisit interval, you can think this way. That is a revisit interval. How much time you want to take to come back to that same target, right? And task scheduling is for example, missile. So if you have tracking missiles, so you want to assign a weapon, like missile. So your tracker is tracking the missile, and then you can send an anti-missile towards those missiles. So that's kind of weapon assignment. So you can assign a weapon based on the tracks and the priority. You can assign the weapon where you want to do that. Okay, that's this one. Okay, this problem I already mentioned that the problem is submarine tracking using sonar buoys. It could be active, passive, and so on. In the same problem, we can talk about sensor subset selection, sensor planning, sensor placement, path plan. So all these can come here, but all of them are based on the tracking results. Okay. Okay. One thing is about resource management. Trackers, once you develop the tracker, you don't need to modify tracker. So you get a new data, new sensor, you do it easy. But the resource management is not like that. If you understand one resource management problem, you can implement that. But when you have a new resource management problem, you have to start again. Okay? So that way, I can't explain all the resource management problem. So what I'm going to do is I am going to take a simple sample example problem. Then you understand that sample example problem and work on it. Okay, that's the idea. So with this, I will show how to do a resource management problem. Basically, what we want to do is all the resource management problem has to be formulated as an optimization problem. Okay, that's the eventual goal. Subject to some kind of thing. Okay. So the objective is that you want to formulate a resource management problem into an optimization problem, then you find a solution for that. Okay. Mostly we spend time in doing this. How to do that properly? How do we do optimal formulation such that it becomes a better answer? Okay. Okay. So in order to do that, let's start with a simple example in which, I don't know, you can see that, I believe you can see. These are the location of sonar buoys. Okay, so there are several sonar buoys. And these are the actual target, not tracks. These are the ground routes. Okay. These are the ground truth, and these are the one. So I'm going to have. This is a constraint you have. At any point, you can use only a small set of sensors. For example, if you have 100 sensors, you can use only 10 of them. Then the question is, which sensor you use and how often you can change. In some problem, you can change every k, right? At k equal 1, you use 10 numbers. At k equal to 2, use another 10. Right? So good. Or in some other case, I would say you can change only after every 4 frames. And mean on you select a sensor, use it for 4 frames. Then you change the different few sensors. Okay? That is what we want to do. The objective is to track multiple targets. Okay, so we want to track multiple targets. So that include initialization as well as tracking. So in order to do that, we are going to formulate this as a. So what we want to do, like if you want to do this, then you have the. I think you guys know CRLB, right? CRLB is J inverse. That's same as P. Okay, you know that, right? I assume you know that. CRLB is a J inverse. J is sufficient information, and that is similar to P. Okay, that is at K. So you have to pick, say, S1 or S2 to you. I simplify the problem. If you use S1, then say you predict the JK plus 1 minus inverse 1 value. If you use S2, you predict this, and if this is smaller, let's say this is smaller than this, then you pick this option, so you pick sensor 2. That's a basic idea, right? You understand that? I repeat that. You know the CRLE at the current time. You'll say if you use sensor 1, you will get there. If you use sensor 2 with this, you get there. And this is smaller, so I would use sensor 2. Right? That is it. So now the question is, how do we do this? Right? How do we calculate this? You understand that? So we want to calculate this. Mainly, I want to calculate this. If you know about CRLP, what are the information that we need in order to calculate it? Anyone? What are the information? So this is the covariance that we have. In order to calculate this, what are the information that we need to know? Intuitively, okay, so you don't need to know anything about the equation. Intuitively, what do you need to know? I say that our sensor location. Okay, which one do we need to know? In order to find this, which one do we need to know? Anyone? R, okay, R is correct. Okay, what is the next one? Do we need sensor location or not? What do you think? Do we need sensor location or not? Let's say this is J, this J, that is like this, right? And so you have a sensor here that is at R equal to 1 degree, okay? And another sensor here, R equal to 1 degree. Do you think they will give the same output or different output? Different output, right? Because this one will have like this, and this one will have like that. So this one becomes larger, right? So the sensor location is also important, right? And how about that? That is the only remaining part. Do we need that or not? Any other answer? the main thing is that this should not depend on that. If it depend on the that, so what do you want to, what you are planning to do? You are deciding which sensor to use. Without using the sensor, you can't get the Z. Is that right? So the Z is a future thing. So you can't do that. You can't use a sensor, then there's no point of deciding which one to use. You already used it, right? So the CRLB is a function of sensor characteristic. It's nothing to do with the Z value. Okay, that's a good thing about CRLB, so that we will use only these two. I don't know, these and H as well to find out the CR. Okay, so that is what you would get. If you know about CRLB, the CRLB is a sum of, this is a prior information. This is the information that you get with all the sensors that you use. Okay, you're adding all the information, take the sum and inverse, that is the kind of covariance. So then this is a covariance, okay? That is like, say, for example, 4 by 4. If you know about optimization, you can't matrix. You want to have a scalar from a matrix. That is why we have trace. Okay, trace will convert a matrix into a scalar value. So I want to minimize the trace. That's like a total error or kind of RMSE. This is similar to reducing RMSE, but through the CR. Okay, so that is how we formulate. And these are the time steps for which we are going to use the same subset. So I will predict, okay, if I use this sensor, maybe the CRLBs will be like this. Okay, and overall, that's the performance of one subset. For the other one, it could be like this, and we decide which one is better, something like that, right? So that is the summation we have here. And then if you go inside this, now we add a binary variable. This is a binary variable. It can take 0 or 1. So this says, if you understand this, say if n is 100 and this is 10, this says, what does it say? This can take only 0 or 1. 1 means we are going to use that sensor. 0 means we are not going to use that sensor. This one says, out of 100, you can use only 10 of them. Okay, so then if you solve this optimization problem, the solution you get this for S will say which sensor to use. Okay, so for example, if the final answer is like this, 0, 0, 1, and so on, then we are using the third sensor. Okay. Okay, that is the constraint that we have. Now, if you go here, so if it is 0, then we don't get any information from that sensor. If it is 1, yeah, we are getting the same information from that sensor. Then we are adding the information that we are going to get. Okay, I don't know whether I have the equations here because I skipped that. Usually that will be something like this. Okay, so then, so you don't use the sensor location directly, but the sensor location will be used in the H calculation. Okay, H is a non-linearized measurement equation, so sensor location will play in calculating the value of H. Okay, so that is how we formulate. So what we did was we formulate this problem as an optimization problem in which we want to minimize the total error. Okay, over all the targets, not single targets. We can have all the targets stacked together, so we want to minimize it. So that is for already existing targets. So for an example, let's go with an output and then we'll see. Okay. For an example, this is a case. Okay, these are the targets. Let's say currently that one target is here, other one is here, the other one is here. So ideally, if you want to pick 10, I would but intuitively, I would pick some sensors here, some sensors here, and here. Are you okay with that? Usually that's what I pick. But this will work to track these 3 targets. That's fine. But how about new targets? Because you know that some new target can appear somewhere here, anywhere. So you have to select a sensor such that you track the targets. In the meantime, if a new target comes, you should be able to detect as soon as possible. In that case, what do I do? In addition to, so maybe I will remove one of the sensors. I will put it somewhere here so that that will cover this area. Right? Similarly, I will remove another sensor. Maybe I will put it here. So that way, so like even if they come around this area, we will detect it. Right? So that's the intuition. So how do we do that? Because this formulation handle only those already existing tracks. For the new tracks, we don't have any CR. Okay, so that is only for existing track. For new track, what we do is we are going to have another objective. So that is why it becomes a multi-objective problem. Okay, so instead of single objective, we are going to have multiple objectives. First objective is the reduce the CRL of existing target. Reduce the CRL of existing target and identify the new targets as soon as possible. So those are 2 objectives that we have. Okay, depending on your problem, you can define what kind of objective that you have and how many objectives you want to have. Then you form it. So I'm not going to talk too much about it because you don't need to know the details. So what we do is, so then we formulate this as what is the probability of detecting a new target? What is the probability of detecting a new target if we use all the sensors? For example, if I go back here, if I pick like this, if the target comes here, what is the probability of detecting it? The target comes here, what's the probability of detecting? You can find, right? Based on the center locations. So if it is here, what is the probability by detecting by this, and so on? Overall, what is the probability of detecting? Okay? That's what we do here. So we decide what should be the PD if we select all these sensors. So this is for a given target location. So we will take particles. So what I would do is, in order to do that, we want to find expectation. What we will do is, we consider what if the target comes here, here, and if it's an equal probability to have targets anywhere here, so you find the PD if the target comes here, PD if the target comes here, you find the average. Right? Or for example, if you know that the new target can come only through this region. For example, so this is an ocean, or this is the only region they can come. Okay? In that case, I will consider only particles here. Then I consider PD for that, and then your solution will remove the selection. Right? It will go towards that area. Right? Based on your prayer, you factor that as well. Okay? Once you do that, then we form this as a combined objective function. This is the first objective we have for the already existing target. And this is a new objective that we have for detecting the new target. And usually we will have a weight here. Reason is that this could be 500 and this could be 0.8. Because one is error, other one is speed. Right? So you can't just simply add without a weight because then most of the thing is going to there. Right? So if it is 500 and 0.8, then which one do you prefer? Like, next option might be say 498 or 0.9. Right? So if you simply add that, you would think that, okay, this is 500 and 500.8. If you add this, this is less than 500, so you would prefer the red one. But I will prefer still you would prefer red one because this is increased, right? But like in this case, this won't happen. That you think that, let's say this is 0.6, okay? Which one would you prefer? I would prefer the black one over the red one. Because in terms of the RMSE, they are close, pretty close. But the PD increase a lot from 0.6 to 0.8. That's a lot. So, but if you simply add, you will not get that. Because that is why we want to give weights. We want to give weights for this and this so that you can just normalize into the same unit. Okay, that's the idea of putting the weight when we solve multi-objective optimization problem. So solve, okay, when we say solvable, right? For an optimization problem, one is solvable mean, do we have a feasible solution, right? That is one question, like, do we have a feasible solution? And then this problem, we have a feasible solution. So if the question is the other way, can we find the optimal solution? That's a different question, right? Solvable means, can we find a feasible solution? Can we find the optimal solution? For this kind of problem, these are NP hard, if you know about that. So you can't guarantee that you obtain the optimal solution. Okay? But you might get a suboptimal solution, might be good enough in most cases. But yeah, in some cases, it may not be feasible. You won't find any solution that satisfies all the constraints. If that's the case, then you have to relax your constraints such that you will get a feasible solution, right? But this one is feasible, right? Is that right? That's the question? Yeah. Okay. But anyway, so you are the one formulating the problem, then you can go back and change the problem in a different way. So it's such that maybe it's easier to find the solution faster, or maybe you can have a slightly better performance as you want. Okay, or for example, it's WB. How to pick it is a harder question. You have to change based on the user requirement. Okay. Okay, this is the one talks about solution technique. Even if you learn about how to solve this problem, it's not going to help you in a different problem because different optimization problems are different. What you may need to do is once you have an optimization problem, most of the time you would use some existing solution technique. For example, genetic algorithm and so on can be used to find some suboptimal solution to this. Okay, but if your research is mainly on optimization, then you have to write a new algorithm to find the solution in the faster way. Okay. So these are called NV hard. That means you can't find the answer in optimal. Any polynomial time. So we find a near optimal solution. I think when I was doing masters, I proposed a techniques to find a suboptimal solution, but I'm not going to talk about it. But anyway, so we will solve sample and we get the output. Okay, so we are going to show the performance of the proposed algorithm. In this one, you see that the scenario omnidirectional sensors. Do you know the meaning of omnidirectional? In all the angles, they are like the same pattern, right? And so the measurement bearing, and sometimes we call it azimuth. Okay, so that's you have to keep that in mind. So I use particle with that at that point. It's nothing to do with the filtering at this point for the resource management. Omnidirectional means it can, like, if you have a sonobuoy here, it can detect the angle anywhere. With the target here or here, you can get the angle, but then the beamforming is there, right? Yeah. Okay, so this is the scenario we talked about it. Then when we use our solution technique, this is what we get. So now, if you are debugging, you will look at the results and see whether it makes sense, right? So this is at K and the next frame, following frame, and so on. If you look at this frame, we have say two targets here. This one is just coming, right? So we didn't do any earlier time step, we didn't have that track. Now it came. The next time, because if you look at this, the error could be like this, but this could be large.
What is the square box?
Pardon?
Square box in
This is a selected sensor. The blue one means that's selected. These are the sensors already there. Okay. So what happened is that in the next time step, we assign more sensors to this. So if you see that, we have more sensors to this target compared to others. So we can justify that because that coherence larger, we are assigning that. Then how do you justify these? New target. So right there, they are assigned to cover these new target, and these can be used to track this target as well as the new target. This also can be covered this region as well. So that makes sense. Okay, so that's what you would conclude, right? Because if you are implementing this, immediately you won't get this result. Then you have to think whether this makes sense or not. If not, what is wrong, and you have to go and debug your code or the optimization problem and see why it's not getting. Okay, next. So that you see, keep on going, right? So if you go going in, and at this time, this is going out. So at this point, it's not there, but we didn't know that it's going out. So we assign. Later on, we realized that okay, that target is not no more. Then that is removed here. Then they are redistributed. So that way, by looking at this, we can say that yes, our algorithm works reasonably well. Okay. This one shows that if you don't consider new target, you may end up in this kind of situation and you won't detect it. That's obvious, right? But if you consider new target as well, then the assignment will be something like this. When a new target comes, anything. Okay, next I will talk about different problem, but I won't spend too much time, but just I would highlight things over here. So path plan, same problem. Okay, now we have transmitters and receivers. So you can consider this way. And transmitters are tipped from an aircraft and they are moved. Okay, so then the problem is, so you have, these are the sonobuoys that you have, and this is the transmitter that you have, these are receivers. Okay, say this is a time k equal to 1, that's the target key. Okay, so what we have to plan the path of this transmitter. Okay, that's what we want. So what do we need to find for the next time step? So what should be the next output? Like if K2, what do we need to find? Because before you formulate the optimization problem, you need to find out what to find. The earlier case, our objective is finding a site. Okay. Now let's say I want to move this transmitter. Path planning is that. Okay, you have to think what do we need to find in the next step? So we need to find the location of this transmitter, correct? Correct? So we want to find a new location of the transmitter. So what we need to find is new location. Are you okay with that? So what are the constraints we have on that new location? So these are the things that you have to think before you start formulating. So we want to find a new location, that's here. What are the constraints on new location? Anyone? Target position goes towards the objective, right? So we use target position so that will the one lead us to where to move. That is the objective. Constraint is different. Constraint means you can't do beyond certain thing, right? So what are the feasible location the transmitter can move?
The reverse detection range.
Okay. Assume there's no limit on that. Okay, for now, assume there's no limit on the receiver tower. Okay, but how would we limit the transmitter location? Okay, I'm asking. Okay, can the transmitter can be anywhere in the circle or can be anywhere in the circle? So two circles. Which circle is a possible thing? So in the first case, I say the next location could be anywhere in the inner circle. In the second case, I say next location could be anywhere in the bigger circle. How do we decide? Which one is correct? Smaller one or bigger one, or how do we decide? That was my first question about the constraint. Which one is the feasible region for the next location? So because that's what you have to think. Because once you formulate that, if I go through my slide, you can understand. But if you are the one going to do it, then you have to think, right? Which one is that? Because we want to optimize. So what do you want to optimize? Like SI means, or do I want to optimize PI? PI might be the new location, right? So what is the constraint on that if you want to formulate that? Okay, let me say this way, okay? That is a helicopter, right? It's going in a helicopter. It's going in a helicopter. So the transmitter is at this point, and the sampling time is 2 seconds. Okay. Can this be 1,000 meters away in the next answer? No. Why? Based on what? Based on maximum speed, right? So you know the speed, maximum speed that it can have, so that way it cannot reach there. So what we use to reduce the radius, decide the radius? Maximum speed times t, for example, or the current speed times t. Okay, that will decide the radius. So it can be anywhere in this area. Okay, that's one. But usually it won't be circle. Usually it could be something like this, only this region. Why? Pardon?
If the helicopter is diving, it cannot turn answers.
Which one is content? Sonar or helicopter?
Helicopter is holding the gun sonar. It cannot take a sharp turn.
Helicopter cannot match up. Yeah, that's the reason, right? So the helicopter cannot turn faster, right? So if the actual helicopter is at this point, if it is going this direction, right, in 2 seconds, with a maximum turn, it can go here, here, or the maximum speed, it can go here. So this is a region, feasible region, right? So now to formulate this problem, instead of finding the new location and putting constraint, I can maybe formulate this as omega and speed. What do you think about this? So we want to find out what should be the omega and what should be the speed. If you know this, then what do you do? So if you have here, then you reach here, right? So then the way of the value that you want to find out this, but the speed should be less than max, V max, for example, right? And the omega also should be less than omega max. Correct? These are the constraints. It depends on the platform types. Some of the platform can move faster, some of them can turn faster, and so on. Okay. So this is what it says. The feasible locations are restricted by maximum and minimum velocities and okay. So where did we use this? I didn't use this. How would you use this one? So if you go back to this figure, how do we use the minimum velocity here? So I put 0 here, but it says some mean V min is there. If we introduce V min, what will happen to this figure? Now we have this, right? We say that if it goes like this, and say we have this. Earlier I said the whole region is feasible. Now I am saying only this region is feasible. So right? Because it can't stay. Helicopters can do maybe, but like here of a plane, for example, plane can stay in one place. But the minimum is not 0, they have to move anyway, right? So that means it cannot be in this region, right? So this is a particular application. What I'm explaining is that how to think. Once you are given a problem, what are the things, factors that you need to consider to improve your formulation so that it becomes more realistic. Okay. So once you formulate that, then it's going through the multi-static formulation and so on, but I'm not going to talk about that. Okay. This work, what we did was in the, so in normal tracking, okay, when we do the normal tracking, always we need to know the receiver location. Are you okay with that? In all these tracking problems, you need to know the sensor location. And always VIM is known. But in the sonobuoy deployment of problem, this is not exactly known. So basically, you deploy from an aircraft, then it floats on the water, but it slowly moves. So then they don't have GPS. So that way it has uncertainty. Okay. So you have a sensor location, but it could be anywhere here. So, and you have another one over here that is smaller uncertainty, then that will affect into total error. So this sensor location error will translate into the track covariance as well. So we'll have a large error in the overall error of the tracks will be large if you have error in the sensor. So we have to factor that as well. Okay, that's what it, this one talks. I'm going to skip that, but that's what it is. Okay, see, this is where we put all the constraints. So like when we put the formulation, we put all the constraints saying that the speed should be great, smaller and constraint. In this one, I went little further and say that constraint on acceleration as well. For example, we use Vmax, right? We use Vmax. But if the Vmax is 100, but the current speed is only 50, maybe you can't go to 100 in 2 seconds. So you have to factor that. Okay, those are the things that we do here. And these are some results. Okay, on the resource management, the last part that I want to talk about is the Markov decision process. Markov decision process is a well-known topic. I have tried it to do some problems. It was success in some of them, but in some of them, it was little harder to use. But anyway, let's talk about what is that. We are going to talk about closed loop and open loop solution. Whatever we studied up to this point is an open loop solution. Okay. So MDP, Markov decision process, that is for a closed loop problem. Okay. MDP is for closed loop and the other problems are open loop. Okay. So now let's understand what is open loop and what is closed loop. Open loop means you say this, like say I want to do certain actions. Okay. So I will do action 1 and action 2, action 3 and action 4. This is open loop says you do this sequence of action and you don't care about the outcome, you do it. For example, I point to, okay, that's the open loop. Closed loop means you say A1, if the outcome is 1 or 2, then you do A2, Otherwise, you do A4. That is the closed loop. Closed loop means take the output, based on the output, you have an option to do what to do. That's a closed loop. You do action, take the observation, change the solution. Open loop is you predefine the solution and do. This is the easiest one. This is what I use in all the cases, but this is optimal one. Optical is closed loop, but that's complicated. Smaller problem, that's okay. Large scale problem, closed loop is hard. Okay. So MDP is a way to achieve a closed loop. For example, this one, right? So there's a target here, another target here. We have two targets, and there's a radar here. And the PD of this target is 0.6. And PD of this is 0.8. That's it. Okay. In the open loop, considering the 0.6, that says assignment is 1, 1, 2, 1, 1, 2, 2. That's it. Open loop, when you solve that, it actually factor that it's a 0.6, so that I may need 2 scans to detect at least 1, and so on. So the open loop gives this as a solution. But if you use a closed loop, what it will do is it will say 1. If you detect it, go to 2. If you miss it, go to 1 again. This is detect and miss. You understand that part? The closed loop solution will say you go to 1 and get the detection. If it's detected, go to 2. If you miss, go to the same target again. That's the idea of closed loop. Okay. So if you understand this, now I am going to talk about Markov decision process. The Markov decision process is, if you want to formulate a problem as Markov decision process, you have to define the state space, states, actions, transient properties, and reward. So you convert this problem into this, then you can use some standard MDP solvers to find the solution. Okay? So let's do this way. So in the MDP, we have state 1, state 2, state 3, and state 4, something like that. You define a state. State could be, one of the state could be a target detected, T1 detected, T2 detected. That could be one state. Okay? T1 missed, T2 detected. These are the state, like possible states that you can, similar to the track state x dot y dot. Usually this could be discrete states and say, okay, well, these are the possible values. This is it. So if by in MDP, what we do is we will take an action here. With certain probability, this can go to this. With some other probability, it will go to this. And we will have a reward for doing this. Same thing here, I will make an action. So then it can go here or here with different probabilities. And then you get reward, and this is another reward. And it goes like this. So when you have a population, so what you do is you first define the state. Again, that state itself is a hard problem. Once you define the state, what are action you do? So usually for MDP, people explain this as the MDP problem that way, so maybe easier. So you have a grid. And there are some blocks here. So you start here, you want to reach somewhere. Okay. So what is the path you want to take? Then the actions are state is the location of in the grid. Action could be move up, down, left, and right. So these are actions you can take. For some reason, but certain probability, even if you want to go up, you can't go up. Assume that. Okay, that is a probability of transition. And if you consider all these, then you define the possible state, possible action. What are the rewards you get when you go from one state to the other? And what is the probability to go from here to here? Okay. Once you define that, I believe it's a little harder for you guys because this is another domain on the resource management that we are going too far. At least I will highlight that so that you can go and read more. Okay. So that is the main MDP part here. So MDP means, so decide an optimal policy. In the MDP, once you do the MDP, the final answer is going to be this, or a table. State and action. So after solving the MDP problem, this is a solution I give to somebody. They, okay, this is my state, I will take this as action. This is my state, I will follow that action. For example, state 1, 2, 3, 4, it says action up, down, down. What you do is, say initially you are in state 2, then your action is down, then say you go to 4, so your action is down, then you say it goes to 1, action is up, and so on, right? So we just follow the policy. So policy is given to you, you just follow the policy based on the state that you have. Okay. So this is a solution technique for MDP. I don't want to talk too much about that. So the challenges with the MDP is that state may not be observed. In that example, I said if you are 1, then go up, then 2, down. Sometimes you don't know, you can't observe where you are right now. The state is not, may not be observable. So then you have to, for example, the state is the actual location, ground truth. Ground truth. Okay. If that is the case, but in our tracking problem, we don't have the ground truth, so we will use only the track. You can consider that. This is the state cannot be observed directly, but we go with some observation and make action based on that. And that is part of the partially observed MDP, if you want to read more on that. Okay. Okay, anyway, so I didn't, okay, honestly, I can say that MDP is a complicated topic for you guys if you want, but I think maybe if you know about machine learning, I think these days people are talking about reinforcement learning. If you heard about that, that is an MDP, version of MDP. Reinforcement learning is a version of MDP. So, yeah, that's why we use it, right? So, MDP is a good technique for certain problems. So, you have to read and understand that. Okay. So, because I didn't want to, like, that's all I have about the resource management. As I mentioned, every resource management is a different problem. You have to go and study about that. Okay. So, if you want, you can take short break and like before till 11 o'clock, according to the plan, we can talk about this. Based on what we studied after this point, how do we solve this problem? Think about it. Okay, let's take 5 or 10 minutes break, 5 minutes break. Think about this and see how we can use what we studied after this